Hi, and welcome to Introductory Astronomy again. Today we're going to be talking about star clusters, looking out into the universe and seeing what's out there with telescopes. So one of the things we notice when we look out in the universe is that there's not just single stars like the sun. In fact, single stars like the sun are the exception. Stars come in bunches, sometimes really big bunches. And these bunches are so big they form into huge balls, sometimes, but sometimes they don't. So today we're going to be going through certain types of clusters, relatively small star clusters called open clusters and big star clusters called globular clusters. So here is a picture of one gigantic star ball, so you can already guess which one this will be. Okay. So first the obligatory slide so that people know if they're stumbling on this, what's going on, or if you're just seeing this out of sequence, you can place this in sequence. This is Introductory Astronomy, actually being taught for credit under the course name PH1600 for Physics 1600 at Michigan Technological University. So this is the 15th lecture in this series, star clusters today. Next time we'll be talking about how stars die, and in particular, black holes. That's one way stars can leave a corpse, is as a black hole. So I am Robert Nemiroff, and if you're taking this course for credit, you need to go to courses.mtu.edu. So what are you responsible for? As usual, you're responsible for the things I say in lecture, supposing they're correct. If not, email me and tell me they're incorrect, and then I'll try to correct them next lecture. You're responsible for the listed Wikipedia entries, but not if they include higher math. You're responsible for the astronomy pictures of the day posted all through the semester, including on quizzes, the APODs from the past week. So if you're keeping score and actually getting credit for the class, you might have gone through homeworks 1 through 7 already, and homework 8 will be released later today and has already been composed. So again, the course action for getting credit is at courses.mtu.edu. So I get email from people who'd like the quizzes released even though they're not taking the course. Now, why would somebody want that? I mean, why would you want to take a quiz? Well, they're kind of interested in what's being stressed, and one person wanted to use these quizzes as I guess, indication of material that I'm stressing for their own course they'd like to teach. But I'm sorry, in order to do that, we have something here called WebCT, which is merged with now Blackboard, and most of the students log on to this, and you need a student password and ID to do that. So I can't easily release the quizzes, sorry. Okay, the Wikipedia entries today are HR diagram, which stands for Hertzsprung-Russell diagram, but Wikipedia will know HR diagram. Cepheid variable, we'll talk about those a bit today. Open cluster of stars and globular cluster of stars. We'll be doing all of these today. Okay, so Cepheid variables are a specific type of star. So we're interested in knowing how far away things are, because we don't know, without just looking at it, we just see the dome of the sky, and we don't immediately know how far away things are. In fact, several hundred years ago, there was thinking that the dome of the sky was just all at some distance. And it was just this amazing tapestry of light that was out there, not all that far away. So now we know that we're looking into a three-dimensional field. And looking into this field, we want to know how far things are away. We want to know what it is we're seeing in the field. It helps us to know how far things are away to know what we're seeing. So if we look in this field of stars, we can see that not all stars are the same. As I mentioned last time with Henrietta Swan-Leavitt, it was noticed that some stars change their brightness, and they change their brightness in a very similar way. In fact, they usually become bright and dim, and on the time scale of sometimes days, sometimes even longer than days. So first they're just a curiosity. Oh, look at the changing star. Isn't it great that our sun doesn't do that, so we wouldn't have extremely hot months and then extremely cool months? But then people realized, in particular Henrietta Leavitt, that these pulsations, these variable stars, some of them appear to have similar spectra, so they all seem to be the same type of star. And also, you can tell how bright, intrinsically bright the star is by how long its pulsation period is. So it turned out that the longer it took for a star to pulse, the more intrinsically bright it was. So very, very bright stars took very long to pulse, particularly if they were of the Cepheid variable class. So then all you had to do is know how apparently bright it was, and you could tell how far away it was. So let's say you see a very long period Cepheid, and it's very bright, apparently bright to the eye. Then that means that it's relatively close by. But more intriguing, let's say you see one that's really dim. It's got a very long period, but it's very dim. What would that tell you? It would have to tell you that this pulsating star, this Cepheid star, is very far away. So it might look like a normal star. It might have the brightness of another star, but to have that long period, it has to be very far away. And that's really useful for calibrating the distance scale of our universe. As I'll say in future lectures, that we're very interested in calibrating the distance scale of the universe, and it's not so easy to do. We have to keep calibrating different distance scales, because what we see on the close by scale isn't what tells us things far away on the far away scale. So we can't see Cepheid variables if they're well across the universe. So we have to use Cepheid variables to help us understand the nearby universe, and then calibrate other standard candles that are then seen far away in the universe to help us understand how things are very far away. So here's a quick YouTube movie of Cepheid stars varying. So here we see the star. You can see the atmosphere contract over here. It pulses and contracts, and over time you can see how the brightness will change. So let's play it one more time. So we can see the outer part of this. We see the outer part of the yellow envelope. And you can see how it relates to the inside of the star. And people analyze why it is that star varies. But we don't always have to know. We just have to know that similar stars do similar things. And then it becomes what's called a standard candle. So a standard candle is something that we can understand how intrinsically bright it really is. Okay, a big turning point in astronomy, we'll talk about this also in future weeks, was found when a variable was found in the Andromeda Nebula. So we know now that the Andromeda Nebula is a nearby spiral galaxy, just like our own spiral galaxy, the Milky Way. But it wasn't always known. There was a big debate, even 100 years ago. There was a big debate as to whether these were just other nebula, gaseous spots on the sky, or whether they were what were then called island universes, galaxies like our own. And so people would look at the Andromeda Nebula, which is the spiral type nebula that's visible to the unaided eye, but of course much better visible with telescopes, and just wonder what it was. And some people thought they could see it rotating. And this is the basis of the Curtis-Shapley debate, which I'll mention in future lectures. But the key point today is that Edwin Hubble found points on this. He had a big telescope, and he was able to resolve points in the Andromeda Nebula. And then he realized that one of these points, or a few of these points, were varying. And he noticed that their variation periods were very long, yet they appeared very dim. So he had this classic quandary that I just pointed out. The only way the period could be that long and it could be that dim is if this nebula was very far away, very far away. And so this was an indication, a key indication, probably the indication that our galaxy is not alone in the universe. It is not the only galaxy in the universe. There are many other galaxies out in the universe like ours, and it was done primarily with Cepheid variables pointing the way. So here we see a Cepheid variable in another galaxy called M100. This was taken with the Hubble Space Telescope. So out here, away from the center of the galaxy, we see expanded in this box a small star that, a star that is not completely resolved, but is not resolved at all. We've only resolved a few stars. But even though it's a point of light, we can see this point of light getting brighter and dimmer. And so this helps us determine the distance to this further away galaxy. And there is a point to which we lose the ability to find Cepheids. And so what happens is, the next rung of the distance ladder is we're lucky to find galaxies that have both supernovae and Cepheids in them. So the Cepheids help us tell how bright the supernovae are when they're at their brightest. And then when we go further out in the universe and we can no longer see Cepheids because they're just too dim, we can calibrate the distances to galaxies by supernova, by how bright the supernovae are. Specific types of supernova, and we'll cover that too. Okay, so now on to other things we see in our fields of stars. So if you look at telescopes, so I actually understand that our 25-inch student telescope has been available for viewing on, might be tonight. It's been the last 2 Wednesday nights. So we have a couple of students who are wheeling it out onto the Fisher Hall deck. And you can see your own field of stars. You can point in any direction and just see lots and lots of stars. You can also see some particularly, I think, globular clusters and even open clusters. There's the Pleiades is visible to the unaided eye. So when we started looking at things, we start trying to understand what they are. And we start trying to make groups of things. So humans are good at making classes of things. So it was noticed that there are lots of clusters of stars, that stars form individual stars. They form into binary stars in multiple star systems. But then it was found there's more than that. There are open clusters, it was found. And they were different than a different kind of cluster called globular cluster. So they were distinct groups. It isn't just they don't just merge between the two, where you have a few stars in an open cluster, and then you have even more stars in a mediocre cluster, and then most stars in a globular cluster. No, it turned out, just from looking, that there are distinct groups. And past the group where there's just a few stars, the binary systems, the multiple star systems, the next group up in terms of how many stars there are called open clusters. And open clusters have very distinct characteristics than globular clusters. So I'll be showing you pictures of each. This will be a good lecture for really cool images. So first of all, open clusters are younger than globular clusters. It is thought that our own sun was once part of an open cluster. Typically, when you see an open cluster, though, you see the brightest stars in the cluster. The biggest blue O and B stars are going to shine the brightest. Most open clusters that we see in our own galaxy are comparatively young. They're less than 1 billion years old. So we know our sun is 5 billion years old, so we're not easily part of a cluster anymore. Clusters, open clusters will disperse eventually, as will globular clusters, but open clusters will disperse on a faster time scale. The light, as I said, from an open cluster will be dominated by the biggest, bluest stars. So we'll see some pictures of that. You can have an open cluster with as few as 10, although I can't think of any which has as few as 10 stars, and as many as maybe 1,000 stars easily visible. Now here's something interesting. Open clusters of stars in our own Milky Way galaxy are found confined to the plane of our galaxy. So we don't see them well outside the plane. So our galaxy is a spiral galaxy, and one can see spiral arms. Well, not as easy as we can see in other galaxies. But across the sky, there's the band of the Milky Way galaxy. And so even though when we look directly out, we can see we can see the band of our Milky Way galaxy. And inside the band, that's where the open clusters occur. There might be some that occur so we're here, here's the sun. If we look in this direction, since we're in the band of our galaxy, we might see an open cluster superimposed on nothing. But the most common case is, and they're very common, open clusters right in the galactic plane. As with all clusters of stars pretty much formed all at the same time. And this is useful for understanding how stars age, what happens to stars as they age. Now, isn't it amazing? All the stars in a cluster would form at exactly the same time. So again, we go back to what we in astronomy mean by same time or same distance. They're not all born at exactly the same time. They're all born within maybe 100 million years of each other or less. So we don't have to know the details of that. It's all approximately the same time. So in astronomy, if things are approximately true, then we consider it, to be true for calculation purposes. So we know so we can estimate what's going on. Some stars in an open cluster might have formed 10 million years before others. And no two stars form exactly at the same time. Just like no two stars are exactly the same, like no two snowflakes are exactly the same at the molecular level anyway. So it's a good approximation that if you see a cluster of stars, it was all formed within 100 million years, and that's approximately all at the same time. They all formed in approximately the same place, too. Now, there might be stars that are superimposed in front of the cluster. So we happen to see a bright star in front of the cluster. They might see a couple stars behind the cluster. So sometimes it's hard to tell which ones are there. But for the most part, most of the stars in an open cluster, you can be pretty sure they're all approximately the same distance. Now, wouldn't it be amazing if they were all confined to this exact sheet, that was all exactly one distance, which is, for one cluster, let's say 137.28489 light years. No, they're not that confined to one distance. They're all within a few light years of each other, maybe 10 to 100 light years of each other. But compared to other distances, 100 light years, 1,000 light years out to the cluster, that's a small amount. 10 light years across is a small amount. So we can say they're approximately the same distance. So it's another useful approximation. This is probably the most famous open star cluster on the sky. It's called the Pleiades. It's called the Seven Sisters. The strange thing is that in some seeing conditions, there are, by some counts, 6 bright stars. So there is a myth as to what happened to the 7th bright star. And we know that star clusters, sometimes stars change their brightness. It's not inconceivable that one of these stars changed its brightness or went behind a thick dust cloud so as to become significantly less bright over the past 1,000 years or so. If with a telescope, though, you can see many more than 7 sisters. You can 7 stars. You can, as in this picture, almost all the bright blue stars you see are, I think all of them are part of the Pleiades star cluster. The Pleiades is a famous symbol. For instance, if anyone has or has seen a Subaru car, particularly the station wagons are particularly common up here because they have all-wheel drive usually. The symbol for Subaru is the Pleiades. I think Subaru might mean Pleiades or 7 sisters in Japanese. So it's a common symbol. Here you see these stars are unusual. How come this star here has this unusual texture around it? Other stars don't. This star doesn't. Well, that's because these stars still have some of the gas and dust surrounding them that they were formed from. Now, some star-forming regions are very active, and you can see stars embedded in pillars that are just becoming visible now. The Pleiades is a little bit older than that. The pillars of star formation, the thick dust of star formation is now pretty much gone. But there is some thin dust there. And so the light here reflects off of this thin dust. And so this right here is a reflection nebula. And it's reflecting the light from the star. Now, the star itself is pretty much blue. So the reflection nebula is going to be reflecting pretty much blue light. So reflection nebulae are usually blue. Another reason why reflection nebulae are blue are the same reason that the sky is blue, because blue light is reflected more easily by the small dust grains than red light. So you're more likely going to reflect the blue. Another thing that most people will notice is that these are not really points of light, they're crosses. Now, how can these stars have these unusual appendages, and how come I never seem to mention them? What are these? These are not at the star itself. The star is a point of light as best we can see. They're not big crosses. What happens is, though, if we look in a telescope, the telescope has these sometimes spider-type crosshairs that hold up the center mirror or the secondary mirror of the telescope. So this is a mirror. Usually it's the secondary mirror of the telescope that's held up. In the way in the background is this big mirror back there. But you need these things to hold up the other mirror. So what happens is light diffracts, coming from the star, diffracts around these things that hold up the mirror. And when that happens, you get diffracted light in that pattern of what it is these spider veins are doing. So that, again, is part of the telescope and not part of the star itself. Stars are points, usually spheres. It's the best we can tell. Recently, there's been a new phenomenon, which I found surprising, in that people take pictures with regular cameras, particularly the Pleiades, which you can take a picture with a regular camera, and you don't need a telescope. So you don't have spider veins holding up your secondary mirror. Yet some of these images have these spider veins on them anyway. And so I found out recently the reason for that is because astrophotographers think that they're pretty. And so they use Photoshop to put them in now. And they change the point spread function, the point function of any point in the field to a point with these things. And so you have to be careful these days what you're seeing, because you can add things digitally that weren't so visible before. But most of the time when you see these crosses, it has nothing to do with a star itself. Stars don't have those. Those are not jets coming from the star. Okay, back to the Pleiades. There's many bright stars in the Pleiades. There's also relatively dim stars in the Pleiades, like our sun, but we don't see them so easily in these kind of pictures because they're just not very bright. The big, massive blue stars are many times brighter than the sun. 100, 1,000 times brighter, and they're just going to light up. The rest of the stars, the more normal stars, probably the more common stars, aren't going to be able to be seen above the din of these very bright stars. Okay, so you can go out and see the Pleiades at almost any time when it's visible, when it's up in the sky, because here is an image taken in 2004 during the Perseid meteor shower. So here's a Perseid meteor in Japan, and it looks like a fuzzy patch at first, but as you look at it, you can start seeing stars. So there's an unusual fuzzy patch. It's not all that far from Orion. There are other star clusters, but this is the one that is most easily seen. So one of my goals in this course is to get people out to see the most easily seen things. So if you're not familiar with the constellation of Orion, you should go out and see it because it's really quite striking. And once you become good at seeing it, when you go out and just happen to look up at night, it just jumps out at you, oh, there's Orion, you think to yourself. And then once you start knowing your way around Orion, you can see the Orion Nebula, you can see Betelgeuse, you can see Sirius, which is near it. Also, that's true of the Pleiades. Once you've seen the Pleiades a few times, you just go out and say, oh, there it is. There's nothing else that looks quite like it. It's not like an airplane. It's not like another star. So it is a cluster of stars, though. And so once you see it with your unaided eye, you can then go get a telescope and look at it and start seeing some of the, more of the stars in there. So it's a good jumping off point. Here is a much brighter, no, not brighter, a much more dense open cluster called the Jewel Box. Now, it's called the Jewel Box because there are bright stars here that are not necessarily blue. There are some greenish stars. There are some reddish stars. So to look at this through a telescope, particularly evident, actually, when you take a picture because your eyes don't perceive, your dark adapted eyes don't perceive color as well as your light eyes. So if you were to take a picture and then look at the picture with your bright looking eyes in a room where you're not dark adapted, you start to see many different colors here. And it's quite striking. Several clusters are like this, but in particular, this is New General Catalog number 290. So way back, Charles Messier made a catalog of things that were not comets, because the big thing back then was to find comets. And he would be embarrassed to pick stuff out that was a comet that wasn't a comet. So it's called the M. So things that are M numbers. So we'll see them now. Like M13 is a globular cluster. I think we'll see that here later. So he made a list essentially telling people, don't confuse this strange thing, M15, which I don't think is interesting, with a comet, which I do think is interesting. Because a couple hundred years ago, comets were all the rage. Nowadays, these M objects we think are very interesting because the comets we find a little bit less interesting. These huge globular clusters we now know are huge groups of stars, and we like to study them. They tell us a lot about our universe. Now, in more recent times, we see too many things with telescopes than Messier, and we're not interested in identifying which ones are comets or not. So the New General Catalog was a more modern effort, and it had, it's thousands of objects in it. And it's not the only catalog of stuff. So in this more modern catalog of things that are not easily visible with a small telescope or the unaided eye, the New General Catalog 290 is an open cluster that has many, many stars, very dense in the center, and many colors, very picturesque. Here's one against a background star field of the Milky Way stars. This is M7. So a Messier object. 7th in the Messier's list. It's an open cluster in Scorpius. Since Messier can only find bright objects, if it has an M number, it makes it particularly interesting. It means that it's very bright, probably visible, possibly visible with the unaided eye. Okay, so this is 2 open clusters. So we can plot stars on the Hertzsprung-Russell diagram. And here we see stars there in the direction of NGC 188. And we can see NGC 188 and M67. So we can see the main sequence here. And we can see the main sequence there. And this is absolute magnitude, so assuming we already know the distance to these things. And what's interesting is that these 2 main sequences, they lie on top of each other here, but over here they don't. So why is that? So after thinking for a while, people did come up with a reason, and it's a very useful reason. It's because these stars, which are missing, by the way, have already evolved off the main sequence. It turns out the more massive stars here, and we'll learn about this in star death more next time, evolve much faster than these stars down here. An O or a B star could evolve completely from being born to dying within 100 million years or so. But these stars down here, so these are the O and B stars. These stars down here, the GK stars, K stars, G stars, they're very stable. They're going to last for billions of years. So they're going to hang out on the main sequence for quite a while. So if you look at 2 clusters, it turns out that all of these stars have evolved off. But for the blue cluster, NGC 188, it's already lost these stars that M67 has not lost. So that's very interesting that that happened. So this enables us to give us a way of identifying the ages of clusters. So we'll talk about that more later. It's the turn-off mass, it's called. And that's particularly useful in dating globular clusters, because globular clusters are so old, some of them, they rival the universe in terms of sheer age. They're really old. Okay, so if you look into the Orion Nebula, star-forming region, you will see in there is an open cluster of stars, and it's called the trapezium. So this was taken by the Hubble Space Telescope. And there's tremendous, interesting structure here of the gas and dust. And there are even more stars forming. So the trapezium is a very young cluster where you can see its birth gas and dust still hanging out and stars still forming. So the trapezium is not done forming stars. Here you can see 2 different open clusters by contrast, happen to be nearly along the same line of sight. Here's one, here's another. This star is unrelated. This is just a star in our own Milky Way. All these other stars are unrelated too. They're somewhere in our Milky Way, but this is a particularly older globular cluster, and there's actually a planetary nebula right there, hard to see. I'll circle it. The star, which is relatively low mass, that has evolved, and this planetary nebula will dissipate in tens of thousands of years probably. Here is a relatively recently formed open cluster, but you don't see its pillars, so it's not that young. It's not still forming stars. It's done that. So the ones still forming stars are the youngest. We'll see pictures of that. This is the next youngest, and this is older. And another way we can tell is by plotting these stars and seeing where their turn-off mass is on the main sequence. Okay, here's, I guess, two more open clusters. This one is nearby. Lots of bright blue stars. This one is getting close to globular cluster mass. I list it as an open cluster, though, so it's actually one of the densest open clusters I've seen. So what happens to stars in a cluster, in any type of cluster? Do they just sit there? And the answer is no. They're variable in a number of ways. Here you see the stars move. So star clusters are essentially big binary star systems. They're all trying to orbit each other, but what happens is they end up orbiting a common center of gravity, center of mass here. So these stars, they're moving most quickly in the center. A typical thing is there'd be a long orbit like this. So according to Kepler's laws, as you might remember, the star is going to move fastest when it's near the center and slowest when it's furthest from the center. So these stars out here, if you watch them, they're going to be moving really slow until they get in toward the center, and they're going to zip much faster. So they are not all in circular orbits. They're not all in, sometimes they're in somewhat chaotic orbits, because once they get near the center, sometimes they can be scattered by a close encounter with another star, and they will be thrown out. So there are stars, as you see, hovering around the edges. So these star clusters are dynamic. They're constantly in motion, and that's interesting. Okay, here is a star cluster where the center part has formed. This is the Rosetta Nebula, which can be seen in visible light to be quite red, and so we feature it in APOD on Valentine's Day usually. And there are stars forming on the edges here. Now what happens is in these star-forming regions is that the stars in the center explode in supernovae and send out shock waves, but they also have strong stellar winds that push out here. So the stars in the center are going to end forming first. And then they're going to push out and create a vacuum in the center and start stopping the star formation of other stars that are forming around here. So you get this big torus where there's spherical shell where things are forming around here, and they're not done forming stars there. Once this star cluster becomes older, it's going to mix up, and these stars are going to be moving by their own thing. These stars are going to be falling to the center. All the gas will be gone. So in a few million years, a lot of the gas will be gone, well, 100 million years or more. And the orbits of the stars themselves will take over. But this star cluster in the Rosetta is just forming now, and is still forming stars, usually in the denser knots that you see. Okay, this is a cool one. This is the Eagle Nebula with the pillars of creation that are so famous. So there's stars forming right in there. The stars forming here. What this is, this looks like an eagle. So here's the eagle's head. See, if there was an eye, it would be here. Here's the eagle's wings. So I don't know if it has feet. What happens is this is a star-forming region where we just happen to be able to see into it. This is an opening of the shell. So there are star-forming regions we can't see into, but this is one we can see into it. And when we see into it, we see the young open cluster of stars all through here. And here's the shell part. And there are these dust sculptures here that are sort of sculpted by the stars. They used to be relatively uniform, but these are the densest knots of gas and dust. And so basically the stellar winds and explosive events push out on these, and they evaporate things. And as the stars themselves form, they evaporate these dust sculptures too. So the Eagle Nebula, we're looking into a star-forming region, a stellar nursery, and we can see its spectacular images in there because we happen to be able to look into a window to it. Okay, moving up to globular clusters. So globular clusters are among the oldest things we've ever seen. And for a while, they appeared to be older than the universe itself, which was a bit of an embarrassment because how can you be older than the universe itself? It doesn't seem possible. Now we know that they're pretty much some of the oldest things, along with shadows of things on the microwave background. They are the oldest things, essentially, that we know, and some galaxies themselves. They contain many more stars than open clusters. They contain as few as 10,000, as many as 1 million or so. Again, we say they're born all at the same time. Again, we say that they all have the same distance. What's interesting about these stars, though, is that you don't see any big, bright blue stars in globular clusters, or relatively few. They're all relatively dim. Why is that? How come there's only these bright stars in the young open clusters? Well, it's again because these young stars, as we'll learn in Star Death next time, they're so massive, and they're so massive, they evolve so quickly that they explode in 100 million years. And so since globular clusters are older, and they've been around for so long, all the big, massive, bright stars have gone, leaving the lots of relatively dimmer stars, many times as bright as our sun, or different than many more than the open clusters. What's interesting about globular clusters also is they're not confined to the plane of our galaxy. In fact, they tend not to like our plane of our galaxy. Randomly, you can find a couple close to it, the plane, but usually, if our galaxy is here, you see the globular clusters orbiting around the plane of the galaxy, not in it. They do have some bright blue stars, if you look closely, there are stars that are relatively bright and relatively blue that appear to be much younger than the globular cluster themselves. And that was a big mystery again, and it was called the blue straggler mystery. Why are the blue stragglers there? People didn't know, but I'll explain why. Okay, so here we see a star-forming region in Rho Ophiuchi, and there is here a globular cluster that's far in the distance. Just a colorful picture. So here is a M3 from the Wind telescope on Kitt Peak. M3 is a globular cluster. You can see many of the stars. They're more red, typically, older, dimmer, more red than stars in open clusters. And it's a big star ball. Here you can see that this is a time-lapse image where there are some stars. If you look at this star, for instance, and this star, and this star, these are variable stars. They're called RR Lyra stars. And they're important for helping to determine distances to some globular clusters. So globular clusters are not only dynamic in the sense that the stars are moving around. The stars move around too slow for us to really see that. But the variability of some of the stars themselves we can see. And that does help us understand how bright and how far away the clusters are. Here's a very pretty photograph of M13, a very massive globular cluster in Hercules. And again, this contains millions of stars. Here's another one, Omega Centauri. I think this is the most massive, densest cluster in the Milky Way. It's far enough away that it doesn't have an M number. If our Earth was orbiting a sun-like star here, nighttime would be very different. Nighttime would have lots and lots of very, very bright stars in it. And in fact, it would rarely be dark as it gets here at night. There's a famous story by Isaac Asimov called Nightfall. He's a science fiction writer, Isaac Asimov. And if he talks about he has a story about a civilization that lives on the edge of a globular cluster. And there's almost always stars in the sky, except every 1,000 years or so, it turns out that the stars align themselves so that it becomes almost completely dark. And when it comes almost completely dark, well, it's a multiple star system that this planet orbits in. And so when none of the multiple stars are there, which is only once in 1,000 years for a few hours, then you could see out and you can see the lots of stars in the neighborhood. And it's a completely different sky. And people go crazy and they go burn down things because they're upset and they don't understand what's going on. And there's a big battle between the people who think they know what's going on and the people who just, now how can people be so excited about, it becoming dark and other stars appearing in the sky, lots and lots of stars? Well, remember, only on the time scale of hundreds to thousands of years ago, people were stopping battles because they saw comets in the sky. So back hundreds and thousands of years ago, when people were much more familiar with the sky, they would study the sky a lot more, and small changes would become big deal. And big changes like that would be an even bigger deal. So only nowadays, when we sit inside and look at our TVs and computer monitors and the sky is so bright it's hard to see stars, are we less excited about changes in the night sky. Although we can see more subtle changes by images over TV and the web. Okay, this is the blue stragglers. So here you see a bunch of blue stragglers in this this NGC cluster image. So it turns out the blue stragglers are, here's an image where there's blue stragglers. Here's a Hertzsprung-Russell diagram of a globular cluster. Here's a tremendous number of stars turning off into here. These stars are evolving, going into there. So the blue stragglers turn out to be members of binary star systems. So in some binary star systems, the gas from one of the stars evolves to become really big and then starts dumping mass onto a lower mass star. When you dump mass onto a lower mass star, it suddenly becomes a much more massive star. And it wasn't that way before. And it starts acting like a young massive star. and it could even go supernova and things like that. So it turns out that stars reinvigorated by their stellar companions are what blue stragglers really are. Here we can tell the age of this globular cluster by its turnoff mass. By modeling how stars evolve, we can estimate how long it takes for a star, just this one star here. So this star here, so how do we do turnoff mass? There's relatively few stars here. Assume there's none. So the star there has now had time enough to evolve and move over to here. So then we figure out how long that would be from the time this thing was born, and that means that this globular cluster must be at least that old. Here we see a globular cluster that is actually very young that occurs in the Large Magellanic Clouds. So we don't have any young globular clusters in our own galaxy. All the globular clusters in our galaxy are really old. They're as old as we know, as the oldest things in our galaxy. But the younger Large Magellanic Cloud satellite galaxy to the Milky Way, it has some young globular clusters. Here's the Sombrero Galaxy from the Hubble Space Telescope. And what's interesting about this is here you see the disk of the galaxy. So we'll be seeing lots of galaxies in future weeks. But if you look very closely, and it's hard to see, there's lots of dots here. Lots of faint dots. These faint dots are globular clusters. So the Sombrero Galaxy has a very rich system of globular clusters. How many are there known in our own Milky Way? There's about 200 known in our Milky Way. So there's many more here. A few more than 200. And that's it. There used to be, well back in the early days of the Milky Way, many more globular clusters. But many of them have been destroyed by encounters with the center of our galaxy and stripped away. The stars have been stripped away. So here we go back to M13. I think it's the third time we're seeing this. It's just an incredibly dense ball of stars. And it is moving about at the center of our galaxy, and when it encounters other star clusters in the center of our galaxy, it will lose stars and will eventually cease to exist. But that won't be probably for billions of years. It has already survived for billions of years. Okay, I'm now going to move to the astronomy pictures of the day. So we'll conclude this lecture and go on to the APODs. So let's go back to the YouTube and go to apod.nasa.gov, if I can spell it right, and it will shift us over to Antwerp, and we will see this image. We will go to the archive, and we will go to a dark pulsar in CTA1. Okay, this is interesting. There's been a new big telescope launched, and it's called the Fermi Space Telescope, formerly called GLASS for Gamma Ray Large Area Space Telescope. It's got similarities to the Hubble Space Telescope, but it looks primarily in the gamma rays. And so it has looked in the position of a supernova remnant called CTA1 and looked at an object that was peculiar and had the attributes of a pulsar but wasn't seen to pulse. But now, in gamma ray light, it is seen to pulse. So it's called a dark pulsar because it doesn't have radio, and I don't think it has pulses in visible light. It's visible in radio and in visible light, but it doesn't pulse in those lights. It only pulses in the gamma ray. So people think that there's a rotating neutron star in the middle of that, and there's a very thin column of gamma rays that goes out on the pole of the neutron star. No, there's a thin column, I'm sorry, got it wrong. Thin column of optical light. The gamma rays are visible in a wider cone. So we are in, as this thing rotates around, we are in the wider cone, but we are not in the optical cone. So we see, as this thing rotates around, we see the gamma rays come toward us every second or so, every few seconds, but we don't see the radio or optical come toward us. Okay, so let's now go to the next one. We're doing a few extra today because we didn't do. This is a spiral galaxy with lots of detail. Our own spiral is not too different from this. These galaxies happen to be in the background. This happens to be in the foreground. So this is just a random superposition. But what's interesting is this NGC 7331 spiral shows a lot of dark dust and a lot of bright blue stars and reasonably well-defined spiral arms. So there's a lot of good texture, spiral galaxy texture there. These galaxies are also interesting. This one has an unusual spiral shape. These have more typical spiral shapes. So we'll be seeing in a week or two that galaxies can be particularly unusual. They're not all easily defined, easily the same. Okay, this is a close-up of the Great Nebula in Orion. So remember, I've pointed out Orion a couple times, and there's a little patch that seems somewhat reddish to the eye, fuzzy reddish patch in the not in the belt of Orion, but just below the belt. And so here's a close-up taken, I think, with a background, with just a backyard telescope, I believe. And here you can see tremendous texture. There's a young cluster of stars around here forming. And here you can see the dust, the tremendously detailed dust. And this is mostly a reflection nebula here in the Orion Nebula, the Great Nebula of Orion. And this is part of a larger region that has lots of star formation going on. Okay, here you see a very loose open cluster of stars superimposed with the last bright comet to come around, well, not come around, but Comet Holmes, to brighten unusually. So Comet Holmes is still out near the orbit of Mars, but is now faded. And at its brightest, it was truly an unusual sight, and you could just go out and look at it in the sky and say, oh, there it is, if you knew where to look. It wasn't so bright that you couldn't help but notice it. That's even more rare. But it was bright enough that if you knew where to look, you can say, without any aid at all, just point to it and say, there it is. And it happens to be randomly superimposed behind stars well in the background. Okay, here's another open cluster of stars forming here, and we can see that the winds from these are pushing out and causing this structure there. It's pushing out the envelope of gas. Here's an opening that I guess stars in this direction looking here would be able to look in there and see it as an open cavity. So this is called NGC 602, and it's very picturesque. Here's another open cluster of stars. I don't know if it's related to this cluster. Okay, here's another. Okay, it just happened to be lots of stars forming. Here's another group of open cluster of stars called Pismis 24, the 24th entry in Pismis' catalog. So this is the Hubble Space Telescope, I believe, took this. Here's a very bright star creating its own little cocoon here. This kind of looks like a strange house over here. I really like this image, because this thing looks like a strange house of star formation. There are stars embedded in there that are very red sometimes, that are forming their own little halos here. And when it gets enough, when these start connecting, then you can get these fronts, and then you get these big cavities. So here's a bunch of stars that have already cleared out the gas and dust around them. Okay, here's an image from a Cassini image of Saturn. So Cassini's been flying around Saturn, taking images of its moons, but also taking images of Saturn itself. So this is an infrared image of the south pole of Saturn. So here you can see many interesting things. Here you can see this tremendous band there. The south pole of Saturn itself is really very strange and has an unusual vortex there that's like a hurricane that's been going on for an enormous period of time. In infrared light, Saturn glows quite brightly, but when it has cloud patterns, these clouds' tendency to be seen in silhouette, to absorb the infrared light and not emit as much infrared light themselves, so they're seen as dark spots. So that's a cloud pattern there. The relatively light spots are relatively underdense areas of Saturn's atmosphere. So there's also a haze seen here that's not seen very close to the south pole of Saturn, and so we're still studying that, trying to figure out why that is. Okay, here we have a nebula that's happens to look like North America. So there's a lot of star formation happening right here where there's dense. Here, there's just not glowing in the nebula. Here it's dark because there's dense, dark dust. So that's a particularly interesting region. And the whole thing glows in red light because the light from stars knocks electrons away from protons, and as they fall back, they emit they emit several colors, but the one that the eye can see the best is red. So that's visible in the North America nebula. And today's image is a bright star. Mirach's Ghost is actually a faint galaxy. This is the ghost here. I'm actually interested to watch how well this does on dig, because it's not, in my opinion, a very spectacular image, but it has an interesting name. So I think its dig popularity is due to how interesting the name is. There's a Beta Andromeda is right here. The second brightest star in the Andromeda constellation is seen from Earth, and apparently bright. But the background galaxy called Mirach's Ghost is there. Okay, I don't believe we have another one. I think that was today. Tomorrow is even scarier, but it's object not found because it will be posted tomorrow. It's tomorrow's astronomy picture of the day, but we will review it next week. And so until next week, I will see you. See you next Monday. Bye.